In this lesson, we're asked to compare the actual area beneath a curve with the approximate integral. Okay, so that would be similar to the previous lesson where we were adding up all those rectangles and we were finding the area using a bunch of those rectangles, and that was the same as the approximate integral, but it wasn't exactly the area underneath the curve. But let's see what it says. It says, given the quadratic equation y is equal to x squared, find the approximate integral, or the area, between 0 and 3 on the x-axis and between 0 on the y-axis and the curve above. The actual area beneath the curve is equal to 9. So they're actually telling us exactly what the area is equal to. So let's go plot this thing. Alright, so it's y is equal to x squared, so that'd be the same as y is equal to 1x squared would be our only term. So there's our quadratic equation like that. It has no intercept there, or the intercept is at 0, I should say. And then we want to find the area, the approximate integral between 0 and 3. So there's 0 on the x-axis, and there's 1, 2, 3. So it's going to be, let me draw this in a little bit. It's going to be between this point here and there. And so it's going to be in this there. So it's going to be this whole area underneath here, beneath this part of the curve. We're trying to find that area like that, and we're going to approximate it just like we did in the previous lesson. Alright, so that gives us an idea. So maybe we can zoom in just a little bit, and just like we did before, let me zoom in like that. We'll get a we'll go get a rectangle. Alright, and let me find a rectangle. I'll move it in over here. Alright, here's a rectangle cruising on in. And alright, well, this would be between 0 and 1, so we need to change that out here a little bit to here. So that would be between 0, there's 1, there's 2, so that's up to the third point, and I'll show it to you just so you can verify that. Let's see. Yep, there it is. There's 3. Alright, so you know it's going to that point up there. Alright, and then I'll zoom back in now. We don't really need to see that third point altogether, but so what we had is, so we have this one big giant rectangle, and it says this rectangle has an area of 27. Remember, this was calculating the area of the individual rectangle from the previous lesson. But this doesn't really work because we have all this space above the curve that doesn't count. So that rectangle is too big, and just like the previous lesson, we'll divide it. So we've divided it into 2 rectangles. We calculate the area of this rectangle and the area of this rectangle, and we add them together, and suddenly the area is down to 16.875. Or let's keep cruising down. We'll make 3 rectangles. The area is down to 14. Still got a bunch of this stuff above the curve that we can't use, so those rectangles are not doing a very good job of approximating the area underneath the curve yet. And let's just keep cranking them out. Let's go up to, say, 10 rectangles. Now suddenly at 10, it's getting there, and now it's saying the approximate integral is equal to 10.395. Well, we know the actual area is 9, but the calculated area using rectangles is 10.395. So let's just see how close we can get with using rectangles. Alright, now I'm up to 15 rectangles, and we're at 9.9 for the area. I'm at 23 rectangles. I'm at 39 rectangles. I'm at 59, 71, 83, 95. And it's starting to fill in at 107 rectangles, and now it's telling us the area is 9.126 using 107, but we know the real area is 9. So let's just see how close we can get by using a bunch more. I don't know how many more I'll use in here. Let me see. There's 120, 132, 148, 164, 184, 204, 224, 244. Now we're actually 9.05, so we got much closer, 9.05. Let's see if we can get the 2 significant digits down to 0. I'm not sure. There's up to 285, 301 rectangles, 337, 373, 393, 413, 473, and when there's 500 rectangles. So using 500 rectangles, we can see by taking the area of each one of those rectangles and adding them all together, it's getting closer and closer to the actual area. Alright, so we're approximating the area. It's the approximate integral is 9.02, but the actual integral is this. When you have an integral, you evaluate the integral and it gives you the area. But I'll show you that in a future lesson where we'll actually calculate the integral and evaluate it. But what we've done, in fact, let me just show you something right here. So for a future lesson, I'm going to put a little integral sign on there. Now you notice this little integral sign? It's kind of curvy on top and curvy on the bottom. It kind of looks like an S. Well, that's kind of what it is, because it really means you're summing things up. Kind of just like this, except there's a what you do is you take your equation y is equal to x squared, and there's a way to turn that into another equation. We say we take the integral and you get another equation, and once you have that other equation, then you can plug in your upper limit and lower limits into that equation and subtract them from each other, and that'll give you the actual area, the real area, and that's how they actually came up with that number like that. But your upper limit would be, in this case, your upper limit would be 3, like this. You'll actually see it like this. This would be 3, and your lower limit would be a 0. You'd have a little, this integral sign would be much bigger, but you'd have a 3 above it, and that would be your upper limit, and your 0 would be your lower limit, and you would call that a definite integral. And they call it definite integral. Oh, I'm going to show you why. It's because a definite integral, and we'll be practicing integrals in the future. A definite integral is because it basically has limits. Definite, see, there's the word define is built into there. So what it is, the limits are defined at the upper end and the lower end versus just having no limits at all. So in this case, the upper limit is 3, like this right there, because that's our upper limit in x, and the lower limit is 0. That's where you plug those numbers in onto that integral sign, and it becomes a definite integral. But we'll actually calculate. You would take the definite integral of x squared, like that, and you would end up with another equation that you would plug your numbers into in order to be able to do it. Well, that other equation, well, I'll just tell you what that other equation is. I'll just clue you in. We won't do it right now, but that other equation is 1/3 x cubed. And maybe you can figure out how I got there. I'll just let that be a puzzle for you right there for now. So that would be your integral, and then you would plug this value into there. So 3 cubed would be 27, and 1/3 of 27 is equal to 9. So you'd have 9 there for your upper limit, and then you would plug your 0 in. So 0 cubed is 0, so that term is equal to 0, and you would subtract 9 minus 0 is equal to 9, and you would actually end up with the real area beneath this curve. Right, so the tricky part is going from the equation to this integral itself. As we say, we take the integral, and then once you have the integral, then you can evaluate it at these upper and lower limits. But we won't be doing that for a few more lessons. We're just better off working with these approximations, because we can see approximations are pretty doggone accurate because of the power of computers. Alright, well that's it for this lesson, and I'll see you in the next lesson.